Hi, welcome to part 2 on inverse functions and inverse relations. I just want to take you back up to this background knowledge that we looked at the start of the first video. I said that the first one and the third one of these, so a one-to-one or a many-to-one relationship, both of those are functions because they pass the vertical line test. Now, I'll just quickly explain the vertical line test. If I draw some vertical lines down here, it will only cross the graph once. Okay, so if I do that to this one as well, it will only cross the graph once for each x value. But if I do it for this one here, it actually crosses it more than once. In this case, it crosses it twice. So this one here is not considered a function. Okay, now what we like to do with inverse relations or inverse functions is we actually want to know when the inverse is also a function as well. So it's not good enough to just have the original function a function. We want the inverse function to be a function. And the way to determine whether the original graph is going to give you an inverse function is that it also needs to pass the horizontal line test as well. So if I look at this one over here, and I draw a line, I might even draw it in a different color. This one I now draw in black. If it again only chops the graph once, it means that the inverse graph will also be a function as well. So strangely enough, in this case, this one will actually give us an inverse function. The original graph wasn't a function, but the inverse will be a function. And this one here won't be an inverse function because it doesn't pass the horizontal line test. So that kind of leads us to the thing that we most want to do in Year 12, and that is we actually want to find when both the original function is a function, or the original graph is a function, and the inverse is also a function as well. Now, the only time that happened when we looked at those previous examples was when the original graph was a one-to-one function. If the original graph is a one-to-one function, then the inverse graph will also be a function as well. Okay, so often what we need to do is we need to restrict the domain of the original function so that it is a one-to-one function. So here's an example. As you can see, this graph here is a function because it passes the the vertical line test, but it doesn't pass the horizontal line test. So therefore that means that the inverse graph will not be a function. However, if we restrict this domain, if we chop this graph in half, or at least we chop it at some point, we can actually make this graph to be a one-to-one function, and therefore the inverse will also be a function as well. So if we change the domain to say r positive, including 0, so from the turning point onwards, or we could do from negative, including 0, it then becomes a one-to-one function. And if it's a one-to-one function, that means that when we get the inverse, it will also be a one-to-one function, or basically it will be a function. So both the original graph was a function, and the inverse will also be a function as well. And this is quite often what we want to do in Year 12. We want both the original graph to be a function and the inverse graph to be a function as well. Now, just one last thing is we do need to note that one-to-many relations will give an inverse that's also a function, but the original one wasn't a function. Okay, that was the second example that we looked at before. So hopefully that's made a little bit of sense. Often we want to restrict the domain so that we get an inverse function as well. The last thing I want to show you is a kind of a special case. This sort of doesn't really fit anywhere, but it will definitely come up in exams and SACs and tests and things. We just seem to like this kind of question because it's actually pretty amazing. If you find the function of an inverse or the inverse of a function, you'll always obtain the variable x. Now again, you might need to kind of replay this 5 or 6 times until you actually understand it, or use the method of staring at it for a really long time. But here's algebraically what I want to show you. Here's my function, it's x squared, and my inverse will be positive and negative square root of x. If I get the inverse of a function, or the function of an inverse, I will always end up with the value x. So what I'm going to do is I'm going to substitute in for x this x squared. I'm going to substitute f of x into this equation here as x. So I get the square root of x squared, which is positive, negative. The square root of x squared ends up just being x. And also, if I do this the other way, I'm going to replace this now, the inverse function, into this as the x value. So I get positive and negative, the square root of x squared, that becomes x as well. So both times I get the value of x. I could do that on another example as well, and I might even do that just down here. If I've got my function equaling e to the power of x, and I get my inverse function, which will now be log e of x. If you don't believe me, then you can have a go at it yourself. Log e of x. Okay, and now if I get, don't know what this random line is, if I get the inverse of a function or the function of an inverse, I'm going to get the function of the inverse. Okay, so that means that I'm going to write e to the power of x, but instead of x I'm going to put log e of x. Remembering from way back from chapter 2, e to the power of log e just equals x. And also similarly, if I get the inverse of the function, I'm going to get, I'll write the function log e of e to the power of x, bring the x down the front, log e of e is just 1, so therefore I get x. The reason that this always works, and in fact it will always work, no matter how complicated the question looks, no matter how difficult it looks, it will always equal x. The reason that it does that has got something to do with the fact that there's a mirror image on this line y equals x. Okay, and so what happens is that each time you get the function of an inverse, you'll end up getting this line over here, which is pretty amazing. But I guess what you need to do is to be able to do all of the calculations, the algebraic calculations to this, and if all else fails, write down a bit of scribble and then write x as the answer, because that's what will always happen when you get the function of an inverse. Okay, so hopefully that helps a little bit. The last thing I will show you, I know the other bit was the last thing, but this is the really last thing, is that we can use our CAS to find the inverse as well. Now, there are other ways of doing this that I'll show you later in class. I've discovered a couple of new ways recently, but they're a bit trickier. So here's the way that I would do it if I were to find the inverse fairly quickly. I'd define my function, say x cubed, and then what I'm going to do is I'm actually going to swap the x and the y's on the CAS. So I'm going to solve f of y equals x for y, and it ends up with y equals x to the power of a third, which is the inverse. For example, I've got this here, the function of x equals e to the power of x, and I've just restricted the domain in this case from x is greater than or equal to 0 just to see what happens. I swap my x and y values, and I end up getting y equals log e of x. But I'm also told that log e of x is greater than 0 and x is greater than 0 as well. Okay, so that it actually took into account my domain, which was pretty handy. So you can actually find out the inverse on a calculator, which is very, very nice. I hope that's made some sense. Now you could probably have a go at exercise 4.6 in your textbooks. Again, if you've got any questions, send me an email. I should be back school very, very shortly, so send me an email and I'll get back to you very soon, or I'll see you in our next class. So thanks very much for watching.